Hey everybody, welcome back. This lesson is about magnetism. Magnetism is one of the fundamental forces of nature governing how particles interact. The magnetic field around a magnetic object is sometimes called the lines of force, or the flux lines. Every magnet has two poles, a north pole and a south pole, and these lines of flux are oriented to those poles. The magnetic flux lines travel within the magnet from south to north, but they also form this three-dimensional field outside of the magnet, and they travel from north to south. The strength of a magnet is determined by the number of flux lines, or what we can also call the concentration of flux lines, which is the flux density. We can see two different examples here. In the example on the left, this is a weak magnet. The weak magnet has only a few flux lines, and we could also describe it as having a small flux density. The example on the right is the opposite. We could describe this as a strong magnet because it has a large number of flux lines, and we can call that a larger flux density. So how do we measure magnetism? Everything has to have units. We can measure magnetism in terms of flux lines, but we can also measure it as the flux density. The measurement flux lines is described like this. It's the absolute number of flux lines. It's measured in units of Weber, which is equal to 10 to the 8th lines of flux. So if we just want to know the absolute number of flux lines created by a magnetic field, we describe it in units of Weber. Another way, the more common way to measure magnetic strength, is in terms of the flux density. We can describe it like this. Flux density is the concentration of flux lines. We measure it in Tesla, which is capital T, or Gauss, which is capital G. Here's an important conversion. 1 Tesla is equal to 10,000 Gauss, which is also the same as 1 Weber per square meter. So here's a perspective on these units and the strength of a magnet. The Earth has a magnetic field with a strength of just 0.0001 Tesla. So Earth is a magnet, but the magnetic strength is very low, relatively speaking. A common refrigerator magnet, as we see in the center example, has a magnetic strength of about 0.1 Tesla. And the magnetic strength of an MRI machine can be significantly higher, in the range of 1.5 to 7 Tesla. So here's an example to make sure that we understand the relationship between these units and measurements. Calculate the number of flux lines per square meter generated by a 1.5 T MRI magnet. You've never seen this before, so let me show you what the math looks like. We'll start with the known variable, which is 1.5 Tesla. We'll take 1.5 Tesla and convert it to Weber. The conversion between Tesla and Weber is 1 Weber per square meter over 1 Tesla. Notice the Teslas cancel out. That leaves us with units of Weber per square meter, and we need to ultimately get to the number of flux lines. So just follow the units. We'll take that number and multiply it by 10 to the 8th lines per Weber, which is another conversion that we know, and all of that together equals 1.5 times 10 to the 8th lines. So 1.5 Tesla is a magnetic strength that creates a total of 1.5 times 10 to the 8th lines of flux. Or to take that out of scientific notation, that's 150 million lines of flux created by a 1.5 T MRI magnet. There are different kinds of magnets. A magnetic field in every situation is created when charged particles within an object, called dipoles, are oriented in the same direction. So we see two examples here. On the left, we have a non-magnetic object, and on the right, we have a magnetic object. And the difference is in the orientation of these charged particles called dipoles. In the example to the left, misaligned dipoles in a non-magnetic object are demonstrated. But in the example to the right, this is a magnet, and this time the dipoles are aligned. So what we're observing is aligned dipoles in a magnetized object. and that is the substantial thing that differentiates between a non-magnetic object and a magnetized object. So this magnetic condition with aligned dipoles can occur naturally, but it can also occur artificially. So let's look at how we distinguish these categories. First, natural magnets. So a natural magnet can include things like the Earth spinning on its axis. Other natural magnetic objects on Earth include lodestones, also called magnetite, which is a naturally occurring material that does have a weak magnetic field. Obviously, the more common magnets are the artificial magnets. One type of artificial magnet is what we call artificial permanent magnets. These artificial permanent magnets are created from iron alloys, and we see these artificial magnets used in compasses, toys, refrigerator magnets. The strongest artificial permanent magnet is neodymium. That's the strongest artificial permanent magnet material. It's called artificial permanent because it's a man-made magnet, but it's permanent. The magnetic field is fixed. It can't be turned on and off. Electromagnets are different, though. Electromagnets are created by an electrical current, usually in the form of coils of copper wire around an iron core. Electromagnets are sometimes called artificial temporary magnets because the magnetic field can be turned on and off by turning the electrical current on and off. Electromagnets are very common, and they'll be discussed in detail in other lessons. Another important topic is what we can call magnetic classification. All matter and materials can be classified by how they respond to a magnetic field, and this ranges from highly susceptible to slightly susceptible. The first category is what we call ferromagnetic. Ferromagnetic materials are highly susceptible to magnetic induction. In other words, they can be caused to be magnetic, and they are strongly attracted to a magnetic field. There's lots of materials like this, especially iron. That's why all of these materials are called ferromagnetic, referring to iron. But it's not just iron, also cobalt, nickel, and the material I mentioned earlier called neodymium. Another type of magnetic classification is what's called paramagnetic. Paramagnetic materials are only mildly susceptible to magnetic induction. In other words, they can't really be caused to become a strong magnet. They're only mildly susceptible to that force, and they are only weakly attracted to the magnetic field. Lots of materials fall into the paramagnetic category. This includes aluminum, platinum, gadolinium, and other materials. These materials are very important because these paramagnetic materials are the perfect type of matter to be used for MRI contrast agents. They only become magnetic when they're inside of a magnetic field. Another type of magnetic classification is what's called non-magnetic. Non-magnetic materials are simply unaffected by magnetic fields, and they cannot be magnetized. This includes a lot of organic materials like wood, glass, but also rubber and plastic. All of these materials are completely unaffected by a magnetic field. And then finally, we have diamagnetic materials. Diamagnetic materials are mildly repelled by a magnetic field, so they're actually pushed away from a magnetic field. This includes several materials such as lead, bismuth, and water. This effect is so small that it usually cannot be detected. The last topic for this lesson is what we'll call the laws of magnetism. The interaction of magnetic fields is governed by these 4 laws. First is the idea of poles. Every magnet has a north pole and a south pole. Even if that magnet is cut into tiny parts, each part will always continue to have exactly 2 poles. So if you cut the north pole off of a magnet, that new piece will then have a north pole and a south pole. Another law is the law of attraction, and here's what that looks like. Unlike poles will be attracted to each other, such as north to south or south to north. Then we have the opposite. That's the law of repulsion. Like poles will repel each other, such as north to north or south to south. And then finally, one of your favorite topics, another important force of magnetic fields is the inverse square law. The force of magnetism is governed by the inverse square law. In other words, the force of attraction or repulsion between two magnetic fields is inversely proportional to the square of the distance between them. So that's a basic overview of magnetism.